Greetings! Welcome to the second lecture on noise. I am Behzad Razavi. Today we will talk about the noise in devices, in circuits, and how we model the noise of these devices for the purpose of circuit analysis and design. So today I would like to accomplish the following. First, I would like to talk about thermal noise in resistors and how we model that, and also eventually talk about noise in MOSFETs. And in the process of looking at noise in these devices, we will also look at some examples of simple circuit analysis as far as noise is concerned. This is just to warm up so that later on when we get to more complex circuits, we have the right foundation and the right mindset for analyzing the effect of noise. Okay. But before we do that, let's just refresh our memory about a few items, a few concepts that were raised in the previous lecture. We saw that we talked about the concept of spectrum or spectral density. And we saw that the spectrum represents the average power that the signal or the noise carries in a 1 Hz bandwidth centered at a given frequency. So for example, at frequency f1, in a 1 Hz bandwidth, we have this much average power. And at frequency f2, we have this much, and so on. Now, in theory, actually, it should not be a 1 Hz bandwidth. It should be an infinitesimally small bandwidth. And if that's the case, then you can see that the total area under the spectrum represents the total average power carried by the signal, because it's across all frequencies. So that's also good to remember. We integrate this area, we integrate this function to find the average power, total average power. Okay, the second concept that we talked about last time and is central to our analysis is this theorem that says if we have the input spectrum to a system, and it's a linear time invariant system whose transfer function is h of s, then the output spectrum is given by the input spectrum multiplied by the magnitude squared of the transfer function. So for example, if we have some sort of noise spectrum coming in and the magnitude squared has some shape like this, then the output spectrum will be like that. And sometimes we say this is a noise shaping function because this noise was shaped like so when it appeared at the output. This theorem is extremely critical for anything that we want to do in relation to noise. Okay, let's now look at thermal noise in resistors. We know that at a finite temperature, the carriers in a resistor have thermal agitations. And as a result, they produce a random noise voltage across the resistor. Of course, the mean value is still 0. So in the time domain, we just see some fluctuations here, and that's hard to interpret. So as usual, we go to the frequency domain and look at the spectrum of that noise. The spectrum of this noise turns out to be flat, white, with a density of 4 kTr, and with a from 0 to infinity. And the way this is modeled is that we assume the resistor itself is now noiseless. And in series with it, we have placed a voltage source. And this voltage source has a spectrum given by this function. So, a few notes. Number one, it is important to understand that the unit of this spectrum is not watts per hertz, but volts squared per hertz. If you remember last time, we said that sometimes we are not interested in the transfer of power. For example, if this resistor drives the gate of a MOSFET at low frequencies, it doesn't deliver any power, but we are still interested in the voltage, noise voltage that it generates. So we are looking at the spectrum of a voltage quantity, and the result is volts squared per hertz. Number two, K is Boltzmann's constant and is given by 1.38 times 10 to the minus 23 joules per Kelvin. It's good to memorize this number. Okay, now in our notation, sometimes we represent the spectrum by S of f. Sometimes we represent it by the actual quantity squared bar. So I may say Vn squared bar is 4 kTr, or I may say SV of f is 4 kTr. Both are spectra per unit bandwidth. There's no difference between these two, so we just interchangeably use these notations. Okay, as an example, suppose R is 50 ohms. 50 ohms happens all the time, especially in RF design, so we're going to use that. At a room temperature of 300 Kelvin, we can calculate Vn squared bar to be this much. Now this looks really small, but this is only in 1 hertz. In practice, we would be interested in much bigger bandwidths. So if you have an amplifier, some high-speed amplifier with 10 gigahertz of bandwidth, we're going to multiply this by 10 to the 10. So suddenly the number is no longer negligible. All right. Sometimes we do something weird. We take the square root of both sides and we write it as Vn squared bar square root equals 0.91 nanovolts per square root hertz. Now this is very strange, right? But alternatively, you can think of it this way. You can say, if I take a 1 hertz bandwidth of this noise, and just that's 1 hertz, and find the average amount of power coming out of that, that would be the RMS value of that power would be 0.91 nanovolts. Okay, the RMS value. So the squared value would be this, the RMS value would be this. So that's another way of thinking about it. All right, the model that we have developed here is a Thevenin model. We could alternatively have a Norton model. So some sort of resistance in parallel with the current source. And to find the spectrum of this current, we say, well, this current times this resistance gives us this voltage. So the transfer function from this current to this voltage is resistance, this R. So what we do according to our theorem is take the spectrum of the current, multiply it by magnitude squared of the transfer function to find the output. So I'm going to write R squared, In squared bar is equal to Vn squared bar, this noise here, right? So from there I can find In squared bar, which is 4 kT divided by R. So this equation and this equation are both useful. Which one we use depends on the situation. Sometimes a Norton equivalent is easier, sometimes a Thevenin equivalent. Okay, so to warm up, let's consider a simple example. Here's a resistive divider that we can consider and try to calculate its output noise. Now to find the output noise of a circuit, we set the input to 0. In this case, the input is a voltage source, so we're going to short circuit the input. And it just happens that we're lucky because now R1 and R2 are in parallel. So we can simply write 4 kT R1 in parallel with R2. That's the output noise of the circuit. All right. Now, but there's something peculiar going on here. Suppose I'm thinking of designing a low noise divider, resistor divider, and this equation says that, well, you can reduce R1 or R2 to reduce the output noise. This equation is symmetric with respect to R1 and R2, but the circuit is not. R1 is in series with the signal path, R2 is in parallel. So we have to think about this more carefully and see how we actually go about choosing the values of R1 and R2. So what we should do is, in addition to considering the output noise, we should also consider the output signal. Because while we are playing with R1 and R2, it is possible that we are doing something to the signal as well. In other words, we should really consider the signal to noise ratio at the output. And for that, we will do the calculations like so. The signal power at the output is given by the input spectrum multiplied by the magnitude squared of the transfer function. So it's a simple divider, so these are squared. And then the output noise is what we have, so that's what we get. Both of these are quantities per unit bandwidth. Okay, so we simplify this like so, and I'm still trying to understand the trends for R1 and for R2. So I'm going to divide the numerator and the denominator by R2, and that gives me this equation. So what this says is that to maximize the signal to noise ratio at the output, we can either minimize R1, which makes sense because that's in series with the signal, or maximize R2, which also makes sense because that's in parallel with the signal. So this clearly tells us how R1 and R2 should be chosen. Now, if you're interested, you can assume that these two resistors reside at different temperatures and repeat this analysis and see what comes out to be. It's interesting because then you cannot use this equation, so things are a little different. Okay, moving on to another example. This time we'll make things a little more interesting by including a capacitor instead of a resistor to ground. And our objective is to find the output noise spectrum resulting from the noise of the resistor. So as usual, because the input is the voltage source, we short circuit this, and we model the noise of the resistor by voltage source, having a spectrum of 4 kTr. And now we would like to find the output noise spectrum. The theorem said that the spectrum at the output is equal to the spectrum at the input times the magnitude squared of the transfer function. So the transfer function of this low-pass filter is just 1 over RCS plus 1. We replace S with j omega, find the magnitude of this complex number, and square it. So here's what we have. The output spectrum is given by the input spectrum times the magnitude squared of the transfer function, and that comes out to be like this. So you can see that this is a low-pass shape, right? As f goes up, this drops. So as expected, the output noise spectrum has a low-pass shape because we applied a white noise spectrum to a low-pass filter. Now, in some cases, we are interested in the total output noise that this circuit produces. And for that, we have to integrate this spectrum from 0 to infinity, meaning this quantity here. And if we do that, we obtain kT over C. kT over C has a unit of volt squared, not per hertz anymore because we integrate it. And it has a certain significance for us because we see that it's independent of R. If R is higher, this spectral density is higher, but the corner frequency moves in and vice versa. And it just happens that they cancel out, so the area becomes independent of R. kT over C is a fundamental limit in many circuits, as we will see later. Okay, let's move on to noise in MOSFETs. We have three major mechanisms of noise in MOSFETs. One is the thermal noise generated in the channel between the source and the drain. The other is the flicker noise of the MOSFET. And the third is the noise associated with the gate resistance, the poly or silicide poly that we have that forms the gate. So we'll look at each of these in detail. All right. Well, let's start with the channel resistance, channel thermal noise. We know that as the charge carriers start going from the source to the drain, they have thermal agitations, and that results in a certain fluctuation in the current carried by the device. In the saturation region, we model this noise as 4 kT gamma GM. GM is the transconductance of the MOSFET, and gamma is a factor which is equal to 2 over 3 for long channel devices and something around 1 these days in modern technologies. So typically we assume gamma is about 1. Okay, now looking at this structure and this model, I ask myself if the noise spectrum is given by 4 kT gamma GM in the drain, do I want to maximize GM or minimize GM? It seems from this equation I should minimize GM, right? Well, okay, so here's how we think about it. Assume that this device is used as a constant current source. So the gate is connected to some bias, and we are only interested in the DC current produced by this device. And unfortunately, that DC current is accompanied by some noise. In that case, indeed, GM should be minimized. On the other hand, if the device carries a signal from the input to its drain, then the story is different. So in this case, if I just go and blindly reduce GM so as to reduce the noise current in the drain, that's true, but then what am I doing to the signal itself? So what we have to do again is find the signal to noise ratio at the output of this device and see whether GM should be maximized or minimized. Okay, so let's do that. We will draw it. We know that the signal current produced by this MOSFET is equal to the GM of the device times the input voltage. So for the signal to noise ratio, we can write the output signal spectrum or signal power is given by GM squared V in squared. So GM squared V in squared bar, right? So remember always the magnitude squared of the transfer function, which is GM in this case. So that is the amount of signal that we have at the output, and then we have to divide that by noise. Both of these are current quantities, and this noise is given by 4 kT gamma GM. So what this tells us is that to maximize the SNR, we have to maximize the transconductance of the device. So the conclusion here is that if the device acts as a constant current source, its GM should be minimized. And if the device acts as an amplifying device, then its GM has to be maximized. Okay, moving on. Let's talk about flicker noise in MOSFETs. We know that the substrate of a MOSFET is a completely uniform and clean crystal, but with all these atoms sharing bonds between them, forming bonds between them. But once we get to the interface between the substrate and this oxide, we lose some of these bonds because we're going from silicon to SiO2. And that means that we have some dangling bonds here. Now, when the charge carriers start from the source and travel towards the drain, sometimes they fall into these bonds. So they get trapped and then they are released. And this trap and release mechanism creates noise. And that noise is not like thermal noise. This is one mechanism by which flicker or 1/f noise is created. Okay, so the flicker noise is modeled by a voltage source in series with the gate, as you can see here. And the spectrum of this noise voltage has this equation, some constant of the technology divided by Cox WL and then 1/f. So you can see that it goes down with frequency. It's no longer flat. So on a log scale, that means that it's a straight line, and the flicker noise of a MOSFET manifests itself more at lower frequencies. So if our signal has components in this vicinity, then we have to worry about the corruption from flicker noise. Okay, the key point here that this equation tells us is that to minimize flicker noise, we really have only one option, and that's maximizing W times L, the gate channel area. And if you look at that as Cox W over L, that's the channel capacitance, the gate channel capacitance. So we really have only one option to reduce flicker noise, and that's just by maximizing the capacitance of the gate source, if you will. So that places certain limitations on low noise design. All right, as an example, let's suppose that our signal resides from some frequency f1 to some other frequency f2. And we have to deal with the noise of this device from f1 to f2 as well. So let's calculate that noise. So we have to integrate this equation from f1 to f2, and that comes out to be like this. So it has a certain relationship. Fortunately, there's a log relationship with respect to the f2 over f1, in a sense the bandwidth of the signal. So even if the bandwidth of the signal goes up by a factor of 10, natural log of 10 is something like 2.5, if I remember correctly, 2.3. So the increase in the noise is not as much as the increase in the bandwidth of the signal. Okay, now one mystery that arises here is what happens if f1 approaches 0? Well, this tells us that the total noise will be infinite. So do we worry about that? What do we do? Well, no. I'll show you an example. Suppose I have a noise component around 1,000th of a hertz. Okay? So that noise component can be approximated by a sinusoid for a short while that has a period of about 17 minutes. That's just inverse of this. In other words, one complete cycle of this noise would take about 17 minutes. So that means that, for example, in a 1 minute interval, so let's say from here to here, the noise doesn't change much. So for example, if I turn on my Wi-Fi system, I send an email for 1 minute and I turn off my Wi-Fi system, during that time, this noise hasn't changed. So it's just like a constant offset, right? And that means that we do not worry about this noise component of 1,000th of a hertz if the observation windows of interest to us are much smaller than 17 minutes. Okay, so you can extend this and see that in reality, in practice, all circuits of interest to us have a minimum signal frequency of interest, below which we are not really worried about the noise. So we really don't worry about the fact that this noise might go to infinity at a zero frequency. Okay. Now, we have both flicker noise and thermal noise in a MOSFET, and somehow we would like to have some feel for the significance, the relative significance of these two. How do we compare these two? One is a voltage source in series with a gate, the other is a current source in between drain and source. So somehow we have to make these agree with each other in terms of dimensions. Okay, well, what I can do is the following. I'm going to AC ground the gate and the source and find the resulting current here, and then also AC ground here and find the noise current here. So we have a noise current here resulting from this voltage source. So this voltage source will be multiplied by Gm squared when it translates to a current here. And then we have a current here which is just 4 kT gamma Gm, that's the spectrum. So now we can compare these two because they are both currents and they're both flowing through the same wire. So if we multiply this spectrum by Gm squared, we get this. And then we have this one as the white noise, so that's this. And then we see that initially, of course, the flicker noise is dominant. It falls, and at some point, it disappears below the thermal noise floor. So as a simple measure of how significant flicker noise is, we extrapolate both of these to cross at a certain frequency Fc. This is called the flicker noise corner frequency. And we use that as just a measure of how serious the flicker noise might be at the frequency of interest to us. Okay, so what we can see from this picture is that if our signal has a significant part of its bandwidth overlapping with this region, then we are picking up a lot of flicker noise. Or if this flicker noise by some mechanism is upconverted to some other frequency of interest, then it may also cause corruption. So depending on the type of circuits that we are analyzing, we might have to deal with either of these mechanisms. All right. In practice, the flicker noise behavior of NMOS and PMOS transistors is not the same. It depends on the technology. In most older technologies down to 40 and probably 28 nanometer nodes, the NMOS tends to have a higher flicker noise than the PMOS device. So here you see the simulation results for two transistors, one NMOS, one PMOS, with a width of 5 microns and channel length of 40 nanometers and the bias current of 250 microamps. And we see that the NMOS noise is higher by a factor of several. So this is at this point like 2.5 or 2.3, and this one is around 7 or so. So a factor of 2 or 3 higher. And then of course at some point the flicker noise disappears, and what we see that is that the gate referred noise of the NMOS is lower than the PMOS because it has a higher transconductance. So we see that the corner frequency of the PMOS noise profile is quite lower than the corner frequency of the NMOS noise profile. The NMOS corner frequency can be as high as hundreds of megahertz, and this is very serious. That means that this device dimension of or channel area of 5 microns times 40 nanometers is way too small if we are interested in signal frequencies in this vicinity. So the device would have to be much larger in area so that this noise, the flicker noise, goes down. Okay, the last type of noise that we will study today is the thermal noise from the gate resistance of the MOS device. The gate resistance arises from just the gate material, typically is polysilicon covered with some sort of silicide, and the resistance is not that small. In finer technologies, this dimension is very small. The thickness of the material is also small, so the resistance tends to be high. We also have resistance associated with the drain and source. We will neglect those for now. Okay, so how do we quantify the noise resulting from the gate resistance? Well, you see that the part of the MOSFET that's over here sees the noise of all of this resistance, whereas the part of the MOSFET that's over here sees very little. So this has to be treated like a distributed system. So what we'll do is we'll approximate this by a bunch of sections as shown here. So for example, we have n sections, each one having a width of 1 over n times the overall width. And then we have these resistances that keep adding up as we go to the last section. Now it can be proved that this circuit is actually equivalent to a lumped model. A lumped model consisting of a transistor with the original width, as we saw, and with the gate resistance that is 1/3 of the total resistance that we have from here to here. This 1/3 arises from the distributed nature of the gate structure. Okay, so now we can calculate the thermal noise associated with RG over 3 and make sure that it's small enough that it doesn't bother us. Now, how do we mean when we say it's small enough? Well, we have to make sure that the thermal noise resulting from RG over 3 is negligible with respect to the thermal noise generated in the channel of M1. So what I have to do is, again, this is in series with the gate, this is in the channel, so somehow I have to bring them to the same domain. So what I will do is I'll take the noise of RG over 3, which is in series with the gate, multiplied by GM squared to convert to a current noise in the drain. So multiplied by Gm squared. And I say this has to be much less than the noise in the channel of the MOSFET. So much less than 4 kT gamma Gm. And we see that that gives us this equation of Rg over 3 much less than gamma over Gm. So that's a simple guideline we can use when we are looking at the thermal noise of a structure like this. Now, in a good design, this must happen. In a good design, the noise of the gate must not bother us. And to do so, we can take some precautions. For example, instead of one finger that is W microns wide, we can fold this device into 2 fingers. Now each of these is W over 2 microns, and they are in parallel, so the total gate resistance is 1/4 of what we had here. So this is very common. Alternatively, or in addition to that, we can contact the gate on the 2 ends by a low resistance material like metal. And again, that also reduces the total gate resistance by a factor of 4. So in general, you have to choose the number of fingers such that the total gate resistance noise becomes negligible with respect to channel noise. And then that's a satisfactory design. All right, this concludes this lecture on device noise models. I will see you in the next lecture.